multiplicatively closed set, multiplicatively closed. And then we had, so then we'll let UP, or US, let's do it, let US be the set of prime ideals. Oh, let's do it like this. Will there be the set of prime ideals Q in spec R such that Q intersect S is empty. Okay, so the claim is the image of the map. Let's do spec of S inverse R, just spec R. So these are the topological spaces. So let's do it like this. The map is bijective onto the map here is bijective onto US. Okay, so it essentially means that spec S inverse of R can be identified with US. Okay, in that so in the map goes from a prime ideal here. Let's call these. I'm going to call these primes later. So so the maps here. It takes this thing to the inverse image of the ideal of an ideal here. So okay, so what is this map? So recall that we have this localization map. All right, this goes from R to S inverse of R in the map. Here, spec of S inverse of R to spec of R. So this is given by taking some Q prime and mapping it to LS inverse of Q prime. So the inverse image of a prime ideal is prime. Okay? And so in the previous class, I stated this and then I proved part of it. I was rushing at the end. So we proved that I think L, so we proved that if Q prime is a prime ideal, then, sorry, if Q, is a prime ideal in R, then S inverse of Q prime is a prime ideal in S inverse of R. Okay, so in the proof was essentially the idea was the following: was that we have to use this, that S inverse of R mod S inverse of Q prime is equal to S inverse of R mod Q prime. Okay, and this is the localization. So what does this actually mean? The one on this side here. So this is the localization of a domain, which is a domain. Which is a domain. Let me say a little bit more about this thing here. So note that S is a subset of R, and here we're localizing R mod Q prime. So just kind of a quick fact here. And tell me if you want me to go back, because I can't, because you guys can't flip through. So if you want me to, yeah.
When the L sub S, like, it takes R to like R over 1, right?
Yep, R goes to R over 1.
And then when you say a prime ideal in S inverse R, that's the usual sense of a prime, but
Yeah, this is a ring, and the quotient needs to be a domain. That's the definition of a prime ideal. If
okay, right.
you quotient out and you get a domain.
Okay.
Yeah. Okay. So yeah. So all I want to say about this is that this this thing over here. Maybe I can even. Well, okay, I'll do this. So let me just do this kind of like a by the way, so S was a subset of R, right? And so S inverse of R mod Q prime, right? So this is the same thing as S bar inverse of R mod Q prime, where S bar is the image of S in R mod Q prime. Okay, so so you're not necessarily localizing. I mean, so here we're localizing at elements of R, but if you look at what the definition says, well, it'll be the same as as modding out by the image of S in this quotient. Okay. So what did I want to prove? So what I wanted to prove is I wanted to prove that this thing. So I showed part of this right last time, but it wasn't quite complete, and I need to show that this is a bijection. Okay. So, okay. So we'll prove. Okay. Prove now that this map that spec RP, or sorry, not P, R S inverse of R to U of S is a bijection. Okay, so to do this, we're going to show that it has a left inverse and a right inverse, right? This map, the left inverse and a right inverse. Okay. All right. So okay. So this part gives this part gives injectivity. This part gives surjectivity. Okay. So all right. So how do we do this? So first we need to show. So for injectivity, so we need to show that for Q, a prime ideal in spec of S inverse of R, that well, that S inverse of L of S inverse of Q is equal to Q. Okay, and so localization will be the left inverse. Okay, so this is the injectivity part. Okay, so let's do this. So the easy part, right? So the easy part is that Q is contained in S inverse LS of S inverse of Q. Okay, so the hard part, we'll focus on the hard part. The hard part is that, well, S inverse L of S inverse of Q is contained in Q. Okay, so okay, so let's do this. So I'm going to omit this. And then let's do this part. Okay, so the proof of the hard part. Okay, so see this. So by definition, LS inverse of Q, right, is the kernel of the map. Okay, and so here's what we can do. We can take R. Okay, then we map it to the ring, S inverse of R, and then we take the quotient here, S inverse of R mod Q. Okay, so the meaning of this is that we have a factorization. So in other words, right, the map here, we have a factorization like this.
Can you go back for a second? Sorry.
Yeah. Keep stopping me when you want me to slow down.
Okay, I'm good.
Q is an ideal in the middle one, right?
Yeah, Q is an ideal in the middle one. Yeah, Q is a prime ideal in the middle one.
Is it a subset?
It's a subset. Yeah, it's a subset. Yeah. Okay. Is that good? You guys have to tell me when I can go back.
Yeah, I'm good. Thank you.
Okay. So so we have this thing and it factors like this. Right, that's how this works. Okay, and then this is injective. Okay, so this is like the first isomorphism theorem. Okay, so but the thing to notice is, so note that the image of S is invertible in S inverse of R mod Q. Okay, so if I had some element of S and I look at it in the target of the top map, or in the target of the top map, those S's are going to be invertible. Okay, so this means by the universal property. So the universal property.
And that's kind of by definition, right?
Yeah, I mean it's because it was already invertible. It's because it was already invertible here, right?
Right. That's where the definition.
Yeah. That's how we constructed it, and so it's going to be invertible in this big image, right? And so what does the universal property tell us, right? So the universal property tells us that we have a further factorization. So we have R. Okay, so we have R LS inverse of Q. Okay, and now we can factor this as S inverse of R LS inverse of Q. Okay, because it's a localization. Or you can take S bar, where S bar is the image of S in R mod LS inverse of Q. Okay, so we have this factorization like this. You could put an S or an S bar. They're both valid. Okay, and so this thing goes like this. This goes into S inverse of R mod Q like this. Okay, and now so we have this factorization. Okay, but we also have that this thing here is isomorphic to, well, the localization respects quotients. So this is S inverse of R mod S inverse of L of S inverse of Q. Okay, and so we get a map like this. Because this is because of the way localization behaves with quotients, and that's what we proved, I think, last time. Okay, but okay, let's call this map alpha, right? Well, because this map exists, this map alpha exists, necessarily this needs to be contained in Q, right? Since the map alpha exists, we must have S inverse, L of S inverse of Q, a subset of Q.
Could you go?
Yeah. So anytime you have a map, so in general, right? So like there's a general thing. Oh, you want me to go back here? Sorry.
Well, those are all. Is something injective there? Then I know you, at the top you have injective. Is that why there's containment?
This is injective here, right? Sorry. Yeah, this is injective here, right? This is the universal property.
That's injective also, right?
This is also injective because this one is a domain.
Like
right?
to put it over the one, yeah.
Yeah, this is injective. This is injective because this thing here is a domain. Because you're modding out by a prime ideal. And the localization at any prime ideal, or localization of any domain is a domain. Right? It is just like adding fractions like you would think normally.
And therefore alpha is injective too.
So I guess because this one's injective, these are both necessarily injective. Right? So both of these maps have to be injective. You can't have an injective map factor through a non-injective map. So like if at some point along the chain, so like you have a map and it's a composition of a bunch of other maps, right? If any of those maps collapse, meaning that if there's anything in the kernel of those maps, right, then the original map had to have something in the kernel.
Makes sense.
So once you have something that's injective, they all have to be injective. Yeah.
Okay, so the fact that you can factor through some other stuff means that all that stuff you factor through necessarily is injective.
Yeah, it has to be.
Including alpha, okay.
Yeah. And the trick that I'm using here, right? So the trick that I'm using here is that, okay, so if you have a map like this, so if A mod I maps to A mod J, so here's the trick, right? Then necessarily I is contained in J. I mean, if these are the canonical quotient maps, there could be some crazy map, this could be like some infinite ring. There could be, but I mean, this is what happens.
Right? So you're just erasing S inverse R essentially
then.
The way you're erasing A,
yeah. A is S inverse of R. Yeah. Is in our application. Okay. So we use the universal property to get the map, and then we use the fact that since you have a map, you get the containment, right? And so that proved the hard part here. Okay. All right. So let's do the other way, right? So that showed that there was a left inverse. Okay. So now let's do the other thing. So, so we proved. So this is like the injectivity part of LS sharp. Okay, if this map here, if we call this LS sharp or LS star, okay. So okay, so then let's do the search activity. Okay. Okay, or the existence of a right inverse, right? So we'll prove that Q prime is equal to LS inverse of S inverse of Q prime. And here Q prime is an element of spec of R. And Q prime intersect S is empty. Okay, so the easy part Okay, so what's the easy part? So it's that Q inverse, so Q prime is contained in LS inverse S inverse of Q prime. This is like a closure operation. Okay, so this will omit. Okay, and the hard part, right, is that the other way. LS inverse of S inverse Q is contained in Q prime. So that means, like, if I localize, the ideal, and then I take the inverse image under the localization map, I that this thing is contained in Q prime. Okay, so let's do the same thing. Well, we kind of start with the same idea. Okay, so we'll use the same ideas. So universal property. And localization commutes with quotients. Like commutes with quotients. Okay, so let's do that. Okay, so let me just pause for a second. Okay, and again, stop me if you need me to pause. Oh, undo. Okay, so all right, so let's do the same thing. So LS inverse of Q of S inverse. Okay, LS inverse of S inverse of Q is the kernel of. Okay, so what do? So we take R. We take it to S inverse of R, and then we take this to S inverse of R mod S inverse of Q. Okay, so it's the kernel of this big composition, right? So in other words, we have a factorization right? R goes into S inverse of R, S inverse of Q. And so like anytime, okay, so by the way, anytime I'm teeing up like kind of this S inverse of R, S inverse of Q, you should expect that I'm going to try and commute them at some point. That's what you should want to do. Okay, so this is, this goes into R mod RS inverse of S inverse of Q, like this. And again, this map here is injective.
What do you mean by commute them? You said you want to commute them?
By commute, I mean, okay, so by the way, so you should be thinking about this being S inverse of R mod Q. Right?
Okay.
So that, okay. Yeah, so it just kind of like distributes.
Okay.
It's nice. Okay. So all right, so we'll show sorry, we're doing Q primes, huh? Everywhere. Excuse me, I dropped my Q prime somewhere. Prime. Okay, prime. Okay, so we're going to show that they're the same. Okay, so I mean, I guess we already had this. So okay. So we also have the following. So this goes, we also have, okay, so let's see. Sorry. So we certainly have this. So I'm kind of running out of space here. Let's see. So we have another map like this. So since Q prime is contained in there, we know that this factor is like so. Okay. And we also know that the image, okay, so we also know the image of S under this map, under, let's say this, I don't know what I call this, let's call sigma, is invertible. Okay, so same with so same with this map sigma bar. So like okay, same with sigma bar and S bar, and S bar, where S bar is the image of S in R mod Q prime. Okay. Okay. So, all right. Okay. Okay. So here's the idea. So we have kind of like two factorizations of this thing, right? So, this is not written the best way. Okay, so let's do it like this. So we kind of have two ways. So we have R, and then we can either localize first. So we can either go to S inverse of R, and then we can go to S inverse of R mod S inverse of Q prime. Or we can go R to R mod Q prime to S bar inverse of R mod Q prime. Okay, and okay, so we have this, and these two things are isomorphic. Okay, and so what I want to do is I want to look at, so suppose that X is and okay, we also have this, right? So we also have that this goes to here. L S inverse of S inverse of Q prime. All right, so we have this, and that this is injective. Okay, so in particular, the composition of all these maps, the kernel of this, so the kernel of this map and the kernel of this map, right? The kernel of the orange maps is this thing, LS inverse of S inverse of Q prime. Okay? Okay, so now here's what we're going to do. Suppose that X is in, so I'm going to suppose that this thing is not Q prime. So suppose that X is in LS inverse of S inverse of Q prime, set minus Q prime. Okay? Right, then, so then it should be, then, okay, I don't know what we want to call the orange map. We'll call this orange map, I don't know, tau. Okay, then tau of X is equal to 0. Right, that's what it means to be in there. Okay, but we know that that tau of X, but we know that this first map, okay, so we need to give these things names, alpha and beta. So, but we know that alpha of X is not equal to 0, because the kernel of this map alpha is Q prime, right? So the kernel of alpha. Okay, We also know that beta is injective. It's the localization of a domain. Right? So this means that tau of x, so in particular, beta of x is not equal to 0. Beta of x bar is not equal to 0. Okay, and so this proves that these two facts here, so these two things here, so injectivity here, so we get that this is injective, and x doesn't map to 0. So this means that you get a contradiction, right? So these things give you a contradiction, right? It contradicts the fact that tau of x is equal to 0. Okay, so that means that these two things have to be the same. So this implies, right, that that this thing, LS inverse of S inverse of Q prime, is equal to S inverse of Q. So let me write that a little bit better. S inverse of Q prime. This must be Q prime. Okay, so we proved now that okay, so let's go back to what we showed, right? So we showed now this thing. We showed that sorry, that was the first part. The second part is this one, right? So we showed that if you localize one of these ideals, and then you take the inverse image under localization, then you get the ideal back, right? We also showed that if you take one of the ideals of the local ring, take the inverse image and localize, you get the ideal back, right? So that proves that that this map here is a bijection. This gives us that this map here is a bijection. And so this allows you to identify the ideals of this ring as the prime ideals of the localization as the prime ideals of this ring, right? Which don't intersect the multiplicative set. Okay, that's what we proved. Do you guys have any questions on that? Okay, so the key points are, use the universal property, right, and use that localization commutes with quotients. Okay.
What do you mean by the universal property again?
The universal property means that if the image of a multiplicative set is invertible in under some ring homomorphism, then it factors through, right? So if S is a subset of R.
Oh, right, then it's universal with respect to that property.
And if you have a map from R to R prime, F with F of S invertible for all S and S, then these things here implies that you have a factorization like that. So this map factors into some FS, and this is the localization at S. So this is the universal property.
Awesome, thank you.
Okay. All right, so let's do another theorem. So we already did part of this. So the theorem, there's a special case. So let R be a ring. And let P be a prime ideal in R. So one, R of P is a local ring. with maximal ideal P R of P. Okay, and 2 that R of P mod PR of P is isomorphic to the fraction field of R mod P. Okay, and so let me just remind you that SP is, so let me put this up here. So SP is RR set minus P, and RP is SP inverse of R. So it's the localization at everything not away from the prime ideal. So it's a special type of localization. Okay, so
that's a notational definition. SP is R minus P.
Yeah. So SP is R minus P. Yep. So these are notations here. Yeah. Okay. So I discussed this one. So this was already discussed. This part.
But the RP wouldn't necessarily depend on S, right? That's like a localization at P.
Yeah, this is a particular S, right? This S is.
Oh, S of P. Yeah, I'm sorry. Okay,
Yeah,
that makes sense.
This is a very.
You just defined it above.
Yeah, so this is the multiplicatively closed set that we're using. Yeah. So yeah. So this is I think we already discussed this. Right. So the idea was that if Q is intersect R mod P is empty, this means that Q set minus P is empty. And that means, so we're using the description that we had previously. Okay. And this means that Q is contained in P. So the idea is that the prime ideals of this localization this localization here are really all the prime ideals that are contained in P, right? All the prime ideals that are contained in that prime ideal P, if you're identifying them as prime ideals of the original ring. Okay, so let's do the proof of 2. So the proof of 2. Okay, sometimes this is called the residue field, since we're modding up by maximal ideal. This is and we're going to give the characterization of the residue field. So first note that PR of P, right? So this is equal to, well, P. I mean, we could do it like this: R of PP. This is SP inverse of RP, and this is SP inverse of P. Okay, so so this is really just the localization of the prime ideal P. Okay, and so now what do we have? So P, so this means R of P mod PR of P. So this is just kind of like one of these things where you're just changing notation to make things easier. SP inverse of this is SP inverse of R mod SP inverse of P, and this is SP inverse of R mod P. Okay, but we claim that this thing here, and this is SP bar inverse of R mod P, where SP bar, so I guess I should put isomorphisms everywhere. This is equal, this is an isomorphism. So now this is where we use localization commutes. And so this is where SP bar is the image of SP, which was just everything not in the ideal, in R mod P. Okay, but SP bar SP bar. So this is just R mod P set minus 0 bar, the zero element. Okay, so so this means so this thing SP, yeah.
If I'm reading that right, you just said that SP bar is the image of SP in itself because SP is R minus P.
Yeah.
Oh, those are different. One's a backslash and one's a forward slash. Sorry.
Yeah. This is the removing the set, and this is quotienting by the set.
Okay.
But this is a subset of R, right?
And then it's image in the quotient.
And the other thing is that this goes to 0 in the quotient.
Right.
So essentially, we're this thing is just the fraction field of R mod P. So this is a domain, so its field of fractions makes sense, and so you can just do this. Okay, so yeah, that's what we have here. So yeah, that's the end of the proof. Right. So we essentially localized the whole thing. I guess a small notational thing. So some notation. So this the fraction field of R mod P, which is also isomorphic to R mod RP mod PRP, is called the residue field. At P. And some people use the notation, so kappa people. So people use the notation kappa of P for this sometimes. Yeah. Okay, so yeah. So what we're going to do next is we're going to do Eisenstein and some irreducibility stuff. And so I'm just going to do some examples of that real quick. And then I think we're going to do Grosvenor bases. And then after that, we're going to move into tensor products. So I guess we have 3 minutes. So I'm just going to end early today. Do you guys have any questions or comments? Okay, well, I'm going to stick around. You guys are free to go. Yeah, turn off the recording now.